Diffraction gratings are optical devices used to produce spectra, for example in spectrometers and monochromators. This plane transmission grating consists of 50 equally spaced transparent slits in an opaque screen. The distance between the centres of adjacent slits is about 0.1 mm. Usually the slit or line spacing is expressed in terms of the number of lines per millimetre, so this one has 10 lines per millimetre. When the grating is used as the diffracting element in this optical system, and a monochromatic line source is used, the diffraction pattern produced consists of a series of sharp line images. The brightest image is the central one. It's called the zero-order maximum. The other images are numbered in order from the centre. If a source emits more than one colour, then an image is formed in each colour in each order. This pattern was formed by using a cadmium lamp that emits 2 blue colours, a green and a red, so there are 4 first-order images, 4 second orders, and so on. The zero-order images all coincide, producing a white line. In the other orders, each image is formed in a direction determined by its wavelength, and every order displays a complete spectrum. Notice that after the second or third order, the spectra begin to overlap. The 4th blue lines turn up before the 3rd red ones. To avoid confusion, many applications of diffraction gratings try to use the first order only. From this diagram, we can see that if the distance between slit centres is d, the path difference between waves from adjacent slits is d times the sine of the angle theta. If this distance is equal to a whole number of wavelengths, the waves will interfere constructively to form a bright maximum when they are brought to a focus. The grating equation summarises the situation succinctly. Maxima are formed in the directions theta given by the equation d sine theta equals n lambda, where n, the order of the interference, is 0 or any positive or negative integer. The wavelength of red light is greater than that of green and blue, so for the first and higher orders, the angles at which the red maxima are formed are greater than that at which the green and blue lines appear. The coloured images of the source are spread out to form spectra in the focal plane of lens 2. Gratings used in analytical instruments are usually designed to use the first-order spectrum. To reveal fine detail in the spectra, they use a very large number of slits very close together. This section of the spectrum of a sodium lamp was produced using a grating with a width of about 2 centimetres, ruled with 1200 lines per millimetre, giving 24,000 lines altogether. You can see that there are 2 yellow lines very close together. These have wavelength 589.0 nanometres and 589.6 nanometres, a difference of only 1 part in 1,000. The weak red and green lines are also double lines. Most practical gratings use reflection rather than transmission and are ruled onto mirror surfaces. To improve efficiency, the lines are angled to reflect the light preferentially into the first order, so that the first order spectrum is much brighter than the others. This type of grating is described as a blazed reflection grating. The sodium spectrum and this section of the cadmium spectrum were produced with a blazed reflection grating.